Good day, everyone. Welcome to this video presentation. Today, we're going to explore an exciting journey into the world of data analysis with a powerful and user-friendly statistical software, the Minitab. Whether you're a student, a researcher, or a professional looking to make data-driven decisions, Minitab can be an invaluable tool in your arsenal.
Throughout this session, we'll walk you through Minitab, showing you how to navigate its friendly interface and get started with its core features. Our goal is to help you confident, turning all that raw data into clear, actionable insights. So, are you ready to unlock the power of your data? Let's get going!
Minitab is a software product that helps you to analyze the data. This is designed essentially for the Six Sigma professionals. It provides a simple, effective way to input the statistical data, manipulate the data, identify trends and patterns, and then extrapolate the answers to the current issues.
So, in this data, we're going to determine which type of paper plane stays longer in the air. So, in order to identify which one, we have to run the data in a randomized way. So now, I'll walk you through setting up our experimental design in Minitab. So before that, I'll show you the data that we had. So this is our data that we're going to input in our Minitab. Once you open the Minitab, is what you're going to see. So the first component at the top is a menu bar. And you'll see a toolbar here. This is the toolbar. So component at the top, you'll see a toolbar here. That is what we call toolbar. So in the toolbar, we have these options here: file, edit, data, calculator, stat, graph, or etc. So to create a fractional factorial design in Minitab statistical software, first let's go to stat. Then let's find the design of experiments, or DOE or DO here. So now let's have a factorial, since we're going to create a fractional factorial design. So let's find factorial. So as you can see, we can see the create factorial design here. So click create factorial design. So this is what you're going to see after clicking the create factorial design. So for this experiment, we will use a 2-level factorial, which can handle anywhere from 2 to 15 different factors, as you can see here, 2-level factorial. So we have two settings in our data, a low and a high setting. So after that, clicking the 2-level factorial design, we can see a number of factors. Since we have the 5 factors influencing our helicopter's flight, we'll enter 5 here for the number of factors. So if you're not sure what resolution you should use, click on display available designs to see a list of designs and resolutions. As you can see, since we have the 5 factors here, we can have the 5-factor column. Then, since we need a 16 runs, or we can choose resolutions 5 to test the 16 runs. So I'll choose resolution 5 here, then click OK. So after you get the desired design, let's go to designs here. So after that, select the design. So I select the resolution 5, as you can see, or the 1/2 fraction. It runs a 16. So resolution 5 that requires 16 runs is better option. So after that, selecting the resolution 5, you can see the number of blocks. So as you set the experiment, Minitab also asks for the number of blocks. Blocks are simply homogeneous groupings of measurement that can be used to account for variation. So the default value is 1, because ideally everything is homogeneous. As you can see, we have the default value here. So let's click OK. After that, let's click a factors to define our design parameters. So first, we have the factor column, the name column, the type column, the low column, and the height column. So in name column, we're going to put the data that we had. So first is the paper type. The next one is rotor, length, leg length, and the leg width. For the last one is paper clip. So let's have the type. Let's change it to text for the paper type and for the paper clip. Let's change to text since we had a text variable here. So for the low, we're going to set for the paper type is light type, and for the high is heavy type. So let's have the volume here. For the rotor length is we have a 7 centimeter, and for the leg length we have 6 centimeter, and for the leg width is 3 centimeter, and for the heavy we have 9 centimeter, and for the leg length we have 11, and for the leg width is 4.5, and the last is yes. Oh, we forgot to put this, so let's put no. So after plotting all the diagram or the table, so let's click OK here. So after that, let's go to the options. So under options, make sure randomize runs is checked. This is a crucial for avoiding bias of our experiment. So let's click OK after that. Then OK to generate the design visual. And now we completed the dialog box, or the Minitab creates the experimental design and displays it in a Minitab worksheet. So the session window above the worksheet provides a description of the selected design with the resulting alias structure. So as you can see, we have the design summary here, or the alias structure here. Okay, and just like that, Minitab generates our experimental layout. So as you can see, we have a 16 unique runs. So each with a specific combination of our factor settings presented in a randomized order, as you can see. So in a column 10, we're going to put a flight time. Okay, here. So this is where the hands-on part begins, since after setting up our design, we meticulously built 16 paper helicopters. Since we have a 16 runs here, so we're going to build a 16 paper, each according to the specifications in our Minitab worksheet. So since we already performed it yesterday, so we already had the data collections for the flight time. So this time I'm going to put the data here. So here. So this is a second. So now that we have our data already, so let's analyze it and see what Minitab tell us. Okay, so analyzing the factorial design, this is where we uncover the insights from our data. So now let's go back to stat again and find the design of experiment, then the factorial. So after that, let's find the analyze factorial design. So here, analyze factorial design. So after that, let's select the flight time as our response variable. Okay, so after selecting that, let's go to the graphs. So under the graphs, we can use the normal plot or a Pareto chart of effects. So you can check the normal if you use normal. Since I'm going to use the Pareto chart of effects, so let's check it. It is to identify factors and interactions that are not significant. So after that, let's click OK. So after clicking OK, let's Minitab give us a NOVA table and these plots notice on the Pareto chart. Okay, as you can see, let's grab this. So notice on the Pareto chart here, let's scroll down. So this is the Pareto chart of the effects. So the bars that across significance lines usually at alpha of 0.05 represent statistically significant factors or interactions. So if you check the normal plot, it also helps us see which effects deviate significantly from the line, but we only use a Pareto chart here. However, with many terms, we might have few degrees of freedom for error, meaning no p-values yet, as you can see, no p-values yet. So this is where stepwise regression comes in handy. So let's go back to analyze the factorial design, or hit the Control E to open your most previous dialog box. Again, let's select the flight time or the column 10 as our response. Then click this stepwise since we're going to stepwise regression, stepwise. So at this time, you can see the method. So this time is none. So we're going to select the backward elimination, which starts with all terms and set alpha to remove. So as you can see, we have the alpha to remove here. The default value is 0.1. So let's click OK. So this time, this helps us find the most parsimonious model. So click OK here. Okay, so backward elimination of terms. As you can see, we have the p-value already. So now with our this model, we can see the p-values in the ANOVA table. So factors with p-values less than 0.05 are statistically significant, meaning they have a real impact on flight time. So that is what you can see after that, analyzing or doing the stepwise regression. So after that, to help you interpret your results, Minitab can also provide main effects and interactions plot. So let's go back to stat again. Click design of experiment. Then find the factorial and the factorial plots. So this is what you can see here. The responses are flight time. Then the variables to include in plots. We have the selected here default, paper type, rotor length, leg width, paper clip. So in significant, main effect and interactions, the main effect plots shows the results of changing from one setting to another for each factor. So be cautious with this. You can only directly interpret main effects that are not involved in a significant interaction. So this is why we only select B and E, because the A combination C interactions overrides the main effects. So here, let's gonna click the paper type, go to available, then leg length, and also the leg width. So we selected the rotor length and the paper clip only, since B is a rotor length and the paper clip is E. So now, after that, let's click OK. So the main effects plot shows we have longer flight times with the paper clip off. As you can see. So, and longer rotor length, the interaction plot shows the interactions between the factors. So this interaction tells us about these two factors. With heavy paper leg length, design of experiments not matter much. With light paper, leg length has a much larger impact. So here it shows us our longest flight is with light paper and short leg length. So to find absolutely best settings, we use the response optimizer. So let's go to stat, then design of experiment, then click factorial. And after that, let's find the response optimizer. So here, the response optimizer. So let's click it. Then after that, select the flight time as the response and set our goal to maximize. So as you can see, I click maximize here. So after that, clicking maximize, let's click OK. Okay, so after that, this graph visually show us the optimal factor setting in red. That will give us the maximum predicted flight time in blue. So based on our analysis, that optimal settings are in paper type is light, in rotor length is 9 cm, and in leg length is 11 cm, and the leg width is 4.5 cm, and for the paper clip on leg is no. So notice that if a factor wasn't significant, it won't appear here. So meaning its specific setting doesn't statistically impact flight time in our model, allowing us to choose based on other considerations.
To sum it up, in order for the paper plane to stay longer in the air, according to our data using the Minitab, it indicates that the paper we should use are lighter paper that has longer leg length with no paper clip on the leg. However, take note that if your plane have the longest leg length, it doesn't mean that it will stay better in the air. A 20 cm leg may be longer, but that doesn't mean that it will be better. The optimal combination of leg length, width, and paper clip presence may vary. And that's all. Thank you for watching, and we hope that you learned something from us. Goodbye!